Hi guys, I just wanted to finish up the lesson from today. So I just want to talk about end behavior model really quickly. There are a few good questions that people asked. I know Amatia was asking one, Sheil asked for the same question, so I just want to clear up some confusion. And the confusion is because this definition of end behavior that I gave isn't the most perfect end behavior model definition. So this is one of the problems from the packet. It is number 17 right here. And I wrote the correct answer down. This is what we went through in class. The right end behavior model is e to the x, and the left end behavior model is x. Pause the video if you need to review this answer or to convince yourself of this answer. So I just want to make sure that you realize the flaw in this definition. This definition says that the end behavior model is a simpler function that has the same end behavior as a given function. So let's talk about, based on this definition, this seems like this could be a right end behavior model. Y equals x. Right? Y equals x. As x approaches infinity, goes to infinity. This function, as x approaches infinity, also goes to infinity. So based on this definition, right, it seems like this would be an end behavior model because these two have the same end behavior. They both go to infinity as x approaches infinity. So that's not what you're looking for. You're looking for, I'm going to graph them really quickly. Here is x plus e to the x. It sort of looked like that. And then here is y equals x. Actually, this came out to be way too far apart, but oh well. It's supposed to be a little closer. Okay, too late now. And this is, let's say, y equals x. So this is y equals x. This is y equals x plus e to the x. The purpose of showing you a calculator and purpose of you using a calculator is to convince yourself that this is not the end behavior model of that. These two for large values for x will not mimic each other. If you did, you look at an x and y table, which I'm hoping you are using, as x goes to infinity, and this is the original, we'll call it y equals x plus e to the x, and this is the so-called end behavior. As x approaches infinity, these will not have the same y value. Therefore, this is not the end behavior model of that. So here's the flaw in this. This just makes it seem like they have to have the same end behavior, and that's not true. Not only do they have to have the same end behavior, they have to grow at the same rate or decrease at the same rate. So I'm going to add, if you want to add it with me, that would be good, so you're not confused. So f of x and g of x, if those two are end behavior models, f of x and g of x grow or decrease at the same rate. That's a better way. That's a better way to, you can erase that too. Yeah. That's a better way to describe the end behavior models. And then the other way is use your calculator to justify. Like these two, if this is truly an end behavior model of that, this should be right on top of each other. Like you can't even tell the difference. The x and y table, the y value should be exactly the same. So this is just sort of like an informal definition. There is a formal definition, which I was trying to stay away from, and I'm still trying to stay away from it, but if you want to look at it, it's on page 74 in our textbook. This is the formal definition of an end behavior model. If you're claiming that f is the end behavior model of g, then you take the limit of f of x divided by g of x, you're supposed to get 1. This is the formal definition of end behavior model. Again, if I thought that we should be using this, I would write it on the board and I would give notes on it, but I think that using this informal one with the fact that they have to grow at the same rate or decrease at the same rate, and combined with, you using your calculator to make sure they match up or they mimic each other, I think that's enough for end behavior models. Okay, thank you for listening. Let's go on to 13 and 14. That's what I was doing when the bell was ringing. I just copied this from 13. And then I copied this from 14. Those are the answers I said in class. And then as the bell was about to ring, I said, what a coincidence that the vertical asymptote of this is 2, and this limit's approaching 2. The vertical asymptote of this is 2, and the limit is approaching 2. I want to give you the definition of vertical asymptote, so pause the video, take out your notebook. This is section 2.2. And this time, instead of like the horizontal asymptote, so the definition of horizontal asymptote, the horizontal asymptote definition, x approach infinity, and the answer was the horizontal asymptote as long as it was a number. Vertical asymptote is switched. X is not going to approach infinity. So x is not going to approach infinity. It approaches the vertical asymptote. The limit answer is infinity. So if line x equals a is a vertical asymptote of some function f, then the limit as x approaches a from the left of this function is some sort of infinity, positive or negative infinity, or the limit as x approaches a from the right of this function is some sort of infinity. This is the definition of a vertical asymptote. I think it's very similar to a horizontal asymptote. Horizontal asymptote, x approaches infinity. The answer is the horizontal asymptote, or x approaches negative infinity. The answer is a horizontal asymptote. If I switch these roles, x approaches the vertical asymptote because the limit is some sort of infinity, and then it approaches it from the right. This is a vertical asymptote. X equals a is the vertical asymptote. This is how you prove something's a vertical asymptote. How do you find it? You just find it using your strategies from Algebra 2. So like a quick example, I'm just going to steal one from the book. There's plenty of problems in the book that said go find vertical asymptote, like this one. F of x equals 1 over x squared minus 4. It said find vertical asymptote. So I'm going to find it using my Algebra 2 strategies, that it's where the denominator equals 0. It's the domain restriction. So we know that x cannot be plus or minus 2. But I need you to show calculus, and actually I need you to go prove it. So we found it using this, and here's the work. So this is the vertical asymptote because the limit as I approach 2 from the left, use your calculator to go find this limit. I promise it's going to be some sort of infinity, positive or negative. And then also the limit, or the limit as you approach 2 from the right, is going to be some sort of infinity. Go find, use your calculator, use the table of values, go evaluate this limit, go evaluate this limit, and you have to do the same thing for negative 2 because they're both vertical asymptotes. And the limit as you approach negative 2 from the left, go find the limit, show it's some sort of infinity, or the limit as x approaches negative 2 from the right, use a calculator, go find the limit. Okay, again, it's supposed to be some sort of infinity. Thank you for watching. Now you can start your homework.